Welcome to the Data Science Institute's virtual seminar series. My name is Dr. Sarah Mackey from Lawrence Livermore National Laboratory. Here at Lawrence Livermore, data science has become an essential discipline in many of our key program areas. LLNL is home to many challenging datasets, as well as home to some of the world's most advanced supercomputers. Our data science staff work in a variety of areas, including machine learning, artificial intelligence, big data analytics, statistical inference, predictive modeling, and uncertainty quantification. The Data Science Institute acts as a central hub for our lab's data science activities. We host events like this seminar series in order to introduce new ideas and potential collaborations to our laboratory staff. We invite speakers from outside the laboratory, from the Bay Area and beyond, to share their innovative approaches with our data science community. We're pleased now to include a wider audience in our seminar series through these recordings. You can read about past speakers at our website at data-science.llnl.gov, or you can email us at datascience@llnl.gov. Thank you and enjoy the seminar series. It's my pleasure today to welcome Mark Sellke. Mark's a PhD student in mathematics at Stanford. He's advised by Andrea Montanari and Sebastian Bubeck. In 2017, he completed his undergraduate studies in mathematics at MIT. And then after that, he received a Master's of Advanced Study with distinction from Cambridge University. He has broad research interests in probability, statistics, optimization, and machine learning. His research is supported by a National Science Foundation Graduate Research Fellowship, as well as a Stanford Graduate Fellowship. Mark has received Best Paper Award and a Best Student Paper Award in the SOTA 2020 conference, as well as an outstanding paper in the NeurIPS 2021 conference. And today we have invited Mark to talk about the outstanding paper that he wrote for the NeurIPS conference. So if you would like to go ahead and take things away, Mark, I'm excited to hear from you today.
Okay, wonderful. So thank you very much for the invitation and the introduction. Thank you to everyone for coming. Can you see the screen okay? Is that working?
Yep.
Awesome, great. Yeah, so I'm very excited to tell you today about a universal law of robustness via isoperimetry. This is in collaboration with Sebastian Bubeck at Microsoft. So in this talk, I'll start by giving some background on kind of what we're trying to think about. I'll tell you some setup for how we think about it a bit more precisely. Then I'll say kind of what is the main result, what does it mean, and then I'll say a little bit about how to prove it. So the starting point, the kind of motivation for what I want to talk about today is really this this picture here. So this is a picture from OpenAI. It's kind of the scale of computation in artificial intelligence over time, and you can see, it's on a log scale. There's powers of 10 on the y-axis, and it's really kind of going up very quickly. In this talk, I'll try to shed a little bit of light on some possible explanation for some part of why this might be happening. So, of course, there are many reasons for what's going on here. We have some explanation for some part of this picture, we think. So to kind of get us on the right footing, let me recall some kind of folk wisdom from classical statistical theory. So if I'm thinking about, as a statistician, of like trying to fit a model to some data, the usual way to think about it is that I want the number of parameters in my model that I'm fitting to kind of be just right. So if I have too many parameters that I'm fitting on my data, then I'm going to overfit. And if I have not enough parameters, then I'm not going to be able to express enough complexity, and I'm going to underfit. So we kind of want some model complexity that's just right. Now, if we think about the extreme of overfitting, that would be memorization. So if we try to kind of fit, if we have n data points, each with some label, and we try to fit each one exactly, that would be memorization. That's kind of as overfitting as possible. And kind of at an abstract level, this is just solving n equations. So probably we need n parameters, just the number of parameters should equal the number of data points. So this should be the like as overparameterized as we would be. Should be as many parameters as we would ever use in our model. But actually in modern deep learning, this is not what happens. You actually use a lot more parameters than the number of data points. So this is kind of the main confusion that we wanted to say something about. So let me show you a bit of what the numbers look like. So first, there's this MNIST data set. This is handwritten digits, like you can see here on the bottom. There's 60,000 of them. And each one has something like 1,000 pixels. And typically, to train a model on this, it's common to use something like 1 million parameters. So this is, 16 times more parameters than the number of images in the data set. That's a lot. As another example, there's ImageNet, where we have these more colorful, diverse set of images. There's something like 1 million of them, and typically a good model will be using something like 1 billion parameters nowadays. And in language, the scale is often even much bigger. We're kind of approaching 1 trillion parameters. So like, why does this make any sense? Now, something I won't focus on today, but which is an interesting line of work towards kind of this same high-level question, is called benign overfitting. And what this story says is that if you're in high dimensions, so maybe the number of data points is comparable to the number of dimensions, then it makes sense to have some amount of overparameterization, to have maybe n parameters or 2n parameters or 10n parameters. Because you're in high dimension, you're not going to overfit too badly. Things will be reasonable. And you get these double descent types of pictures where there's kind of the underparameterized regime on the left. So the number of parameters is not so big. Things get better. So the error, which is the y-axis, goes down. Then it goes back up again. This is kind of overfitting. But then it goes back down again. There's this double descent, and that's kind of the modern ML regime. When you have a lot of parameters, that somehow helps again. And you can do certain calculations to say that this should maybe describe high-dimensional linear regression in models like this. The message I want to explain today is kind of a different story. I'm going to argue that overparameterization might be mandatory, and it'll be really a lot of overparameterization. It won't be, number of parameters on the order of the number of examples. It'll really be a lot more, which is kind of in line with the numbers we just saw for things like ImageNet. Okay. So let me say informally what the main result for today will be. So it's called the Law of Robustness, and it's going to tie together the following 3 commonly observed features in modern deep learning. So the first one is overparameterization, as I've been talking about. The second is memorization. It's common to essentially memorize your training data. And the third is that there's often a struggle with adversarial robustness. So often, if you look at clean test data, you get very nice generalization, but your model is very brittle to small input perturbations by an adversary at test time. And if you can be robust against such small perturbations, then this is a very desirable feature for the model. It means it's not very brittle. So the standard picture for adversarial examples is something like this. You have this picture of a panda, you add some small noise that a human can't detect, and well, the computer thinks it's something totally different. So what the law of robustness says is as follows. So we're going to fix a reasonable function class, script f, and it's going to be described by p parameters. And this can be a very general function class. It can include something like a deep neural network just fine. Okay, and then we're going to construct our data set in a random way. We're going to sample n data points IID from a truly d-dimensional distribution. So it's nice. This has a nice theoretical description. It's general enough so that we might hope it applies to things like images. And then we're going to add some label noise. So we're really going to try to memorize In particular, we're going to try to fit the labels perfectly, including the label noise. Why? Well, deep learning often tends to memorize. So we'll assume that it's memorized. Then the result is that if we want to have any shot at memorizing these labels within our function class and with a Lipschitz function, which means that we're going to be robust to input perturbations, then the number of parameters has to be very large. It has to be at least of order n times d. So the number of examples times the dimension. So this is saying that extreme overparameterization by a factor of the dimension is necessary if you want to memorize robustly. Okay. So I'll, of course, say much more about what I mean precisely, but maybe I'll stop for any initial questions. Okay. So yeah, so let me start by explaining a bit, what do I mean here? So first, let me say a bit about this model of memorization. So we're gonna have our inputs. They're gonna be n independent random points, and for now, let's just say they're uniform on a d-dimensional unit sphere. So we'll allow a bit more generality later, but let's just say they're uniform on a sphere. And I want to say that the number of points n and the dimension d are kind of polynomially related to each other. So they could be proportional. That one could be like the square or the cube of the other, but they should be kind of, not crazily exponentially different in size. Okay, and the labels are going to have some noise. So they're going to have possibly some signal, g. So that's like some deterministic function, plus some noise. And the noise is kind of important. So the noise should have some typical variance, at least sigma squared. Now we're going to be interested in memorizing, which means that we should be fitting the labels perfectly. So a memorizing function is going to fit these labels perfectly for every point in our data set. And actually, we don't need to be so stringent. It's fine if we have partial memorization. I just want to force our functions to fit some of the noise. So for instance, if the mean squared error of a function is kind of well below the level of the noise, then I'm happy counting that as memorization too. Okay. So next I need to tell you what I mean by robust. So I'm going to say a function from d dimensions to one dimension is robust if it has a small Lipschitz constant. So as a reminder, this means that for any two inputs x and x prime, the difference in the function values is bounded by some constant L times the distance between x and x prime. And I want L to be kind of ideally independent of the dimension. It should just be a constant like 5 or 10 or something. And the idea here is that if I have a Lipschitz function, then it's automatically robust to adversarial perturbations, right? So it means that if I change my image by a little bit, then the opinion of the deep neural net is not going to change too much. And so we're just going to use this as our definition of robust. So this is a somewhat strong definition. You could hope that, maybe there's a few regions where things are not Lipschitz, and that's kind of still okay or something. But it's a very nice thing to work with mathematically. It's kind of a worst case notion of robustness. And what I want to point out is that I'm keeping everything on the same scale. So this dimension-free guarantee is really something I can hope for. What I mean by this is that my inputs are on the unit sphere. So they're kind of a constant distance from each other. And the labels are of constant size. So it really makes sense to hope for a dimension-free Lipschitz constant. For instance, the points xi on the d-dimensional sphere will be separated from each other by at least some constant distance. So there's always going to exist some robust function, some Lipschitz function that memorizes these label values yi exactly. So in fact, there's a nice explicit construction where you just use a sum of bumps. So the idea is, well, because my data points are spread out, I can just manually put kind of a nice smooth bump function around each input xi, and just scale it appropriately so that I get the right output yi there. And I'll just put a bump around each input I'm trying to memorize, and then I'll perfectly memorize my data set. And it's kind of a very canonical way to do so. However, there's a downside here, which is that this is using a lot of parameters. So in some sense, this is sort of a trivial way to memorize, but it's not a very efficient way to memorize. In particular, to specify the memorizing function f I'm using, I need to actually use n times d real number parameters to specify it, because I have to give it every coordinate of every input point xi in my data set, which is kind of surprising, because we really want to be memorizing with just n parameters when if n is the number of points. Like that should be at most the number of parameters that you need. And it'll turn out, this is kind of a version of our main result, that no function class is more parameter efficient. So there's no like recipe for constructing a memorizer that's more parameter efficient than this. But let's see what this means in terms of what do I mean by parameter counting exactly. So the way I want to formally set this up is that my function class script f consists of a bunch of functions from d-dimensional space to one dimension. And when I say it's described by p parameters, I mean that every function in the class has a corresponding p-dimensional parameter vector, which I'll call w. And I'm going to impose some regularity requirements. The first one is that the parameter vectors should be bounded by some reasonable value. And the second is that the parametrization itself should be a little bit Lipschitz, a little bit smooth. So if I change the parametrization vector w a little bit, the function doesn't change very much. And the value j I'm using in these regularity requirements, we're only going to have a logarithmic dependence on it. So as long as it's kind of polynomial, it's fine. So these are really very mild requirements. And this is kind of necessary to prevent pathologies. So if I don't have any requirements like this, I can take a real number, I can look at all of its bits, I can kind of extract infinitely many like bits of information from it. So I can do anything I want. But if I have a little bit of continuity requirements, then suddenly like having only one or two real numbers available is really a constraint. So
question.
Yeah, sorry.
Yeah, so can you tie this to the structure? Say if the function class is coming from a neural network, so how do the depth, width, or whether I have fully connected or convolutional layers, how do those things affect these regularity requirements?
Yeah, I'm about to discuss some examples like that. So maybe I'll do that, and then I'll see if that answers your question.
Okay, thank you.
Yeah, great. That's the right question to be asking. How does this kind of abstract setup match up with what you're really working with when you think about deep learning? So as a first example, let's look at linear regression. So here, I'm just thinking about linear functions. So what I'm going to do is I'm going to say that each function is a function on d dimensions. The space of linear functions on d dimensions is itself d-dimensional because it's an inner product with some other vector in the same space. So that means I have d parameters if I'm thinking about linear regression. And so I'm just gonna, in terms of these regularity requirements, I would need to require that the linear function is not going too crazy, and the second requirement just kind of means I'm restricting to inputs x, which are also of reasonable norm. So if I'm thinking about data on the unit sphere or something, then definitely both of these are very fine. Now let's look at neural networks. So as a reminder, what's a neural network? I'm going to have some linear functions, capital Wi. I'm going to apply them alternately with some coordinate-wise nonlinearity, something like, for example, the ReLU function or something else. So in the setup, what's my parametrization vector? Well, let's say that the nonlinearity alpha is fixed. I'm just going to use a ReLU network. Then my parameter vector W is just going to encode all of the entries in all of the matrices I'm using. So every connection in my neural network, there's some trainable parameter there. That's one of the parameters in my parametrization vector. So just kind of every real number that appears anywhere, that's one parameter. If I have a convolutional neural network, then if I write it out in matrix form, there are going to be a lot of repeated entries. And this kind of nice abstract definition of the number of parameters in a function class handles that very nicely, right? So I can just kind of put the number one time into my parametrization vector little w, and then I can put it many times into the matrix I'm using in my neural net, and that's totally fine. Now, what kinds of Lipschitz constants are we going to get in terms of connecting to these regularity requirements? Well, it turns out that basically the relevant quantity is the product of the operator norms of these weight matrices. So that's going to be very reasonable for a neural network with bounded depth, because we're only going to have logarithmic dependence on this product. So this product is something like the Lipschitz constant of something, but we're only going to have logarithmic dependence. So kind of really all that's going to matter is the number of terms in the product, which is the depth of the neural network. So in connecting to neural networks, there's some dependence on the depth, which is still pretty mild, and there's kind of logarithmic dependence in everything else. Now, on the other hand, this product of operator norms is something that is often explicitly controlled in deep learning for other reasons, because if this product is large, then often the gradients are large during gradient descent training, and that's bad for other reasons. So that's kind of the situation. Yeah, let me know if you have any more questions about this point. I can go into more detail on something else if you'd like.
There's another question in the chat. Is there is this saying that you can't do better than a thin plate spline?
So what is a thin plate spline exactly? I'm not sure about the...
Robert, if you'd like to unmute and provide a little bit more detail for your question, if you're able to do so.
Can you hear me?
Yeah.
Yeah, it's just another, it's like a bump function that gives smooth results and has n times d parameters.
Yeah, I guess so then. It sounds like it's maybe sort of similar to the example I was talking about. Is that right? Okay, yeah, great. So what was the name again? Maybe I should know this name.
Oh, it's a thin plate spline. They use it a lot in some image reconstruction stuff I used to do, because it gives universally smooth results to like arbitrary like control points in images, blah blah blah.
Okay, awesome. Yeah. Thanks very much. So I guess that's right then. So I guess the surprising thing is you might think there should be something else you can do, because you're just solving n equations when you're fitting in data points. But yeah, somehow you really need n times d parameters. Okay, great. Yeah, please let me know if there are more questions, but I'll keep going for now. Okay, so it turns out there's kind of a trade-off that you get if you're thinking about size versus robustness. So if you don't care about robustness, then you can just get away with n parameters, because again, you're solving n equations. You really just have to be able to do this if you have n parameters. And in fact, you can even do this using like a 2-layer neural network. So if you care about doing it using deep learning, that's still fine. And on the other hand, as we've seen, we can we can memorize in a robust way using n times d parameters because we have this bump function construction. And it's hard to do better, and so there's going to be a general trade-off. So I want to say that there was a conjecture the previous year before what we did that basically conjectured this trade-off for two-layer neural networks. So what happens here is that you can prove some interesting partial results. For example, you can say that I'm going to think of a polynomial as a special case of a neural network. So if my nonlinearities are like quadratic or cubic activations, I can make a quadratic or a cubic polynomial using a neural network. So I can sort of just think that I'll think about my function classes like degree 2 or degree 3 polynomials. And if I'm in d dimensions, then the number of cubic polynomials is like d cubed. So I have some nice conjecture there for this trade-off. So you can do that. Already you get some very difficult problems if you're thinking about sparse polynomials, though. So if you think about maybe low rank matrices, then you can do things because matrices are nice. You have eigenvalues. But if you generalize to low rank 3 tensors, it already seems quite hard. There's just some very weird things going on. So we still don't actually know how to answer some of these problems. But it turns out that restricting the parameters to be reasonably sized really saved the day for us. And I think this is a completely reasonable consideration if you're trying to model something practical, because exponentially large numbers are just kind of not so realistic. So what we can show is that if we fix a function class described by p parameters of reasonable size, polynomial in the dimension, then memorizing the labels is not going to be possible unless the Lipschitz constant is at least of order square root nd over p. And this factor sigma here is the amount of noise in the labels. So I'm requiring the labels to be at least a little bit noisy, and that requirement appears here as well. In particular, as a specific case of this trade-off, if we want to have a dimension-free Lipschitz constant that's really of constant order, then we have to have at least n times d parameters. And moreover, and something I really like about this result, the assumption that we have kind of uniform data on the sphere, which is very nice theoretically, can be relaxed a huge amount. You just need to have a mixture of less than n over log n components, each of which has some isoperimetric property, which you can think of as meaning that it's truly high dimensional. And also the label noise can be pretty flexible as well. It can kind of be different for different points. It just needs to have some expected amount of noise. And moreover, this result is kind of best possible in terms of n and d because you can do the same bump function construction after projecting down to an intermediate dimension. So that doing that for different intermediate dimensions gives you kind of this full trade-off curve in the other direction.
Another question.
Yeah.
Does your result also cover the classification case? Because maybe I'm confused, because here your outputs are also real.
Yeah. So this is very much for like real valued outputs, I guess. So if you have classification, then your function is not going to be continuous, right?
Yeah.
So
that would still be open.
Huh?
That would still be open to address classification problems.
Yeah. I'm not sure what a good version of this would look like then, because it seems much harder to have a nice notion of being like robust when your function is discontinuous, right? Like maybe you want to say like the kind of surface area of the interface between the different values is not very big, right? But I guess we don't have a nice way to make this result say something about classification.
Would another way to say it to be that if you have the robustness as described in here, then you would also have robustness to classification, but like this condition might be too strong than what's needed for classification?
So
is this sufficient but not necessary?
I think it's just not clear to me how to formulate an analogous statement for classification, because I'm really doing things in terms of a Lipschitz constant.
Yeah.
And if your function is plus minus one value, that doesn't really mean anything, right? Yeah, so I'm not sure. Yeah, it's a very interesting question to try to figure out what the right way to formulate such a statement would be, though. But I'm not sure. So let me say what I mean by isoperimetry. So I said just before here in this second bullet point that the distribution of my covariates doesn't have to be uniform on a sphere. It can be anything that's a mixture of kind of less than n isoperimetric distributions. So I want to think of isoperimetry as meaning that I'm like really, genuinely, truly high dimensional. And kind of there are a few different definitions in math, but the most directly relevant one is that a probability distribution mu on d-dimensional space is isoperimetric if for any Lipschitz function on d-dimensional space, the values of the function concentrate very well over this distribution mu. So for example, what does it mean that things worked for the unit sphere? It means that if I have any Lipschitz function and I look at its distribution of values on the unit sphere, then this distribution is very tightly concentrated with tail behavior as shown here. So this tail behavior is sort of Gaussian tail decay with a standard deviation of 1 over square root of the dimension, because there's this d in the exponent. So that's kind of characteristic of high dimensions. So you can think on the unit sphere in d dimensions, what's a Lipschitz function? Well, it's just looking at like the first coordinate. And typically the first coordinate will be of order 1 over square root d. So kind of this function, all the action will be happening in this 1 over square root d region. And it turns out that this is true for like a general Lipschitz function. And moreover, there are a lot of distributions besides uniform on a sphere that satisfy such a property. So there's things like Gaussians, blah blah blah, but there are other things like manifolds with some nice curvature, or Gaussians plus a little bit of independent perturbation, things like this. And kind of more abstractly, there's something called a log Sobolev inequality that guarantees such a property. So it's really a common property to have in high dimensional space. For example, definitely you can think that your data might live on a manifold of some intermediate dimension. So how can we try to interpret what this means? Well, I think uniform on a sphere is a bit much to assume for trying to model real data, but a mixture of reasonably high dimensional distributions I think is very reasonable. So you might think, okay, first of all, there's a cat component, there's a dog component in your set of images. You can make it somewhat more fine-grained. Maybe you can get away with like 1,000 components kind of like this, and you get something reasonable. And the components, as I just said, they might live on a lower dimensional submanifold. So kind of naively, if I have an image with 1,000 pixels, then I need to say it's 1,000 dimensional. That seems a little fanciful, but maybe there's a lower dimensional manifold of realistic images, and we'd like to say that the law of robustness statement might still hold with some kind of effective dimension like that. And this leads to all sorts of interesting possibilities. You can try to estimate the effective dimension some other way. You can try to extrapolate between different data sets, all kinds of things like this. The other thing that I need to interpret is what is the noise. So first of all, in the kind of abstract setup I'm working with for memorization, there needs to be noise. Otherwise, there's nothing to learn. So if there's no noise in the data set, and I want to think how many functions in my function class do I need? Well, I just need one function because I know what the labels are going to end up being. So I kind of don't need any parameters. You can only start arguing that you need parameters when you don't know what you're going to be trying to memorize beforehand. So that's what the noise is accomplishing. Now, in real life, I think it's reasonable to think of noise as kind of the complicated part of the function. So maybe there's some like linear part that's kind of simple. You can get some amount of learning just with a linear regression, but there's more complicated parts that there's kind of no natural inductive bias for. So there's been a lot of work on inductive biases of different learning algorithms. A convolutional neural network is kind of set up in a way that it'll detect certain patterns. If there's something to learn that's not particularly of that form, maybe it's just noise. There's also something called the long tail hypothesis that I think is very much related, which says something like, from a pre-learning point of view, a lot of the data set is going to look like noise. So maybe 10% of my data set consists of images that are kind of isolated points in image space. There's no other images in my data set that look like that one. From the point of view of any reasonable learning algorithm, I just have this one point floating around all by itself with some label. I'm just going to memorize it because that's all I can really do. So this has been used as an argument for why memorization might be a good thing. And it also kind of ties in nicely here. Let me show you what kind of prediction you can get by using the law of robustness. So this will be a very back of the envelope prediction just to kind of show that we're operating at a realistic scale here. But maybe give me some error bars of a factor of 10 or more in the numbers I say. So first off, let me say some numbers that are more concrete and we sort of know, which is if you look at MNIST, these are the black and white handwritten digits I showed at the start. So here there's 10 to the 5 images in the data set approximately, and there's approximately 10 cube pixels. And if you look at getting good robust accuracy, you want something like 1 million parameters. And so this is a paper by Alexander Modry and his group. They found this kind of, you can sort of see a phase transition here in terms of the accuracy. And the place where the accuracy goes up like crazy, that's something like 1 million parameters. So what I'm going to do is I'm going to say, well, 10 to the 6th, the number of parameters, that's quite a bit less than 10 to the 5th times 10 to the 3rd. But this might be because there's an effective dimension. So if I just fit the law of robustness anyway, I just say that P has to equal n times D, then I solve for D is 10. So the effective dimension, according to this result, should be 10. And you could also think that there was this factor of the noise level sigma, maybe that goes in there too. But I'm just going to make the calculation very simplistic for now. But then what we want to do is we want to scale up to ImageNet, which has more pixels and more examples. So we're just going to keep this scaling factor of 100 that we use to get from the naive dimension to the effective dimension. We're going to scale everything else up. And we end up with the prediction of 10 to the 10 parameters as what we should be using for robust ImageNet. And this is actually on the sort of scale that reasonable models are, like recent models are doing. They're currently using maybe 1 billion parameters, and this is just a little more. So so this suggests that just increasing the number of parameters even by another factor of 10 or 100 might be very helpful for getting robust ImageNet classification.
Sorry, this is again, just to resolve my confusion here again. Now you're talking about classification, which is the reason I asked you earlier about robustness for classification. So could you tie it back to your earlier comment about your law of robustness applies only to continuous functions, but here you're talking about a classification problem.
Right, sure. So I guess what I would say is that, like, I think usually if you look at how you do classification, what you do is you get some real number scores for, how much like a cat is it versus how much like a dog is it, and then you just threshold anyway, right?
Correct.
You say, does it look more like a cat or a dog? So I'm just saying that, at least mathematically, it's much easier to not do the thresholding step. I guess basically I would say that, it's another thing that where there might be some issue, you could imagine there's a difference. I don't see a particularly strong reason to expect there to be a difference. Yeah, I would just say that, we have some setup that we want to be working in. There are a bunch of different choices of setup, which have different, small quirks and issues. And we would hope or expect them to not behave too differently in reality, right?
Jairam, I just in the chat posted a quick sketch that if you go for the real valued function and apply to classification, you should be able to show that it's sufficient at least. Maybe not necessary, but sufficient.
Oh, yeah, let me use. Yeah, sorry, what do you mean by sufficient?
As in, like, if you have the Lipschitz condition, you can then, and you've able to memorize your data by translating the classification problem to a real valued problem, then if you know your noise and you know your epsilon, or your sigma and you know your Lipschitz condition, you should be able to calculate a bound on what epsilon you can handle. Just based on the fact that you will be thresholding and you know what that is.
Let's see.
Yeah, so, yeah, I'm not sure I follow this, because for label noise for classification, what do you mean by that in this setting?
I guess the premise here is that our classifier is going to be thresholding based on a real value, and if that real value function is Lipschitz, we could define our classifier to be robust in that sense.
Yep.
So I think the issue is that if you're like, let's say I have a function that's not Lipschitz, but it's real valued, then I can just scale it down so it's just all the numbers involved are very, very small. And then if I threshold it, I'm basically increasing the scale of the function back up to a constant again. But the Lipschitz condition doesn't mean anything once the scale of the function is very small. So I think that's basically the reason there's a technical issue. It's because if I have a Lipschitz function that's operating with numbers like very close to 0, let's say, then if I threshold it to be positive or negative, I'm blowing it back up again. Yeah. Like if you kind of assume that won't be happening, then the result will sort of intuitively transfer. But I mean, I think sort of from the viewpoint of proving something, like you just can't really say much about, what happens if you have a function that just has like tiny little epsilon fluctuations, but magically thresholding it makes it perfect. Like that just kind of you don't have any stability, and you're trying to reason using stability. Anyway, I'll keep going. Yeah, it's a good point that there are these issues for sure. So let me say a bit about how the proof goes in this setting. So I'm going to simplify things. So I'm going to say the labels are pure noise. The labels are just plus minus ones. The labels we're trying to memorize. And you can just think the data is uniform on the sphere. And I'm going to assume that the labels end up being reasonably balanced, which means that at least a third end up being +1 and at least a third end up being -1. So this is really a proof step. this is some kind of assumption that holds with extremely high probability, and I'm only going to assume it once. Okay. So now I want to memorize these labels, which are pure noise, and I'm going to use this isoperimetry property. And what it tells me is that if I have any fixed function in my function class, so kind of any fixed deep neural network that I might try to use, and it is Lipschitz, then either it's -1 on a very small amount of the state space, or it's 1 on a very small amount of the state space. So for instance, if I have a Lipschitz function on the unit sphere, it can't be both 1 a lot and -1 a lot. One of them, it has to be very, very rarely. So for example, if my Lipschitz function is 10 times the first coordinate, then it's going to be 1, and 10 times the first coordinate, and then I kind of clip it to be between -1 and 1. I can always do that. Then the function is going to be 1 when the first coordinate is at most a 10th. Or sorry, is at least a 10th. And that's like exponentially unlikely in high dimensions. So what this means is that, well, the function is very unlikely. It's like e to the minus d unlikely to output one of these two labels. But to perfectly memorize, it has to output both labels at least n over 3 times. So it has to do something that's e to the minus d unlikely n times or so. So basically, it's e to the minus nd unlikely to be a good memorizer that fits these labels, because it has to do something unlikely a lot of times. So, okay, we've just seen that each individual function in our function class, like each individual deep neural network, which is robust, fits the labels with a low probability. And we're just going to union bound over the function class. And what this means is that the function class needs a lot of distinct functions in it to have a good chance to memorize. It needs at least e to the nd functions. Otherwise, I can just say that by a union bound over my function class, there's no way to have a good memorizer. And this balanced label assumption I made was only used once. That's kind of technically important. And okay, if I have p parameters, then basically I just have an e to the p-sized function class if I discretize. So this is possible because I have polynomially bounded parameters. I have some amount of smoothness in my function class. But kind of the main thing that enters here is the number of parameters. Everything else just kind of contributes on a lower order. So that's really the idea of the proof. You can add some ingredients to it in a few ways. For example, for mixtures, you basically assume balanced labels within each component. So as long as you have like as long as you have like a super constant number of data points per component, you can get balanced labels per component, and you're fine. The result also has a generalization perspective. So as you might know, there's a notion called the Rademacher complexity, which implies kind of uniform concentration generalization results over learning for some function class. And classically, a function class will have Rademacher complexity, something like the number of parameters over n, if you're looking at n examples. So this is some classical way to say that if you have a reasonably sized function class, you're not going to overfit too much. And an interpretation of our result is that in this setting with Lipschitz functions and this isoperimetric property, the Rademacher complexity improves to have some dimension appearing in the denominator. This is nice because it makes the result kind of more general. For example, it lets you say that there's nothing special about looking at the mean squared error in terms of measuring your overfitting or your memorization. You can kind of use anything reasonable in place of the squared error, and you're going to get the same type of result. This also has a nice the Rademacher complexity lets you phrase the proof in a nice way. Maybe let me skip over this. Let me finally say before concluding that there's a way you can do things with a depth 3 neural network where if you allow kind of arbitrarily large weights or arbitrarily large parameters, the result doesn't hold. But this uses some weird stuff. It uses like a very weird non-Lipschitz, non-explicit nonlinearity inside. And something I think is kind of a nice puzzle is, does the law of robustness hold for something like a ReLU network if you have unbounded weights? So the idea would be that ReLU network is a pretty reasonable object, even if you have unbounded weights. If you have to have a reasonable Lipschitz constant coming out, there's not that much craziness that can happen under the hood. So I'm not sure about this. I think it's a nice puzzle. Some more open directions I'm interested in are, everything I said so far was kind of implicitly about the Euclidean norm. Kind of abstractly, you just need some property that ensures this sub-Gaussian tail decay. You need some definition of isoperimetry that ensures that Lipschitz functions concentrate. I'm not sure if there's some nice class of settings where this holds, for instance, for like Wasserstein distance. So if you want to think of an image as like a set of black masses on some like two-dimensional grid, you could try to set things up that way, but I'm not sure how that norm would affect things. It would also be nice to refine the notion of robustness. So I talked about the worst case value of the Lipschitz constant. It's natural to look at things like the average value of the gradient norm or the squared average gradient norm. These actually don't work, simply because in this simple sum of bumps construction, or thin plate spline, as we've learned that it's called, the function is constant except on an exponentially small amount of the state space. So if you do something like average, you're going to get a very small number. You really need to take the maximum gradient value. So I'm not sure if there's something else that can be done. It would also be nice to look at what happens with different specific architectures, specific other settings, or to take training dynamics into account instead of just uniformly controlling over a function class. So I think there are a lot of directions such as these that I'm pretty excited to think about, and maybe some of you want to think about too. So thanks very much for your attention, and let me know if there are any more questions.
Thanks, Mark. This was very interesting. Does anybody have any questions for Mark? You can feel free to unmute or type in the chat if you prefer. Okay, I do have a question for you, Mark. This is probably a pretty naive question, as I'm not deep in the details of this research as you are. But so the input data points, you're drawing those from a distribution. And so I may have missed it, but is the conclusion of your work also a probabilistic statement about my ability to memorize robustly?
Yeah, sorry. Yeah, basically it's saying that if you don't have enough parameters, you're going to fail with high probability.
Okay, that intuitively sits better with me. I missed the probabilistic conclusion.
Yeah, sorry. I didn't say that part, but yeah, basically so the idea of the proof was, you say each individual function in your function class kind of is a good memorizer with a very low probability. So kind of by a union bound, what you end up showing is that with a kind of exponentially small probability, there's an exponentially small probability for any function in your class to memorize well if you have too few parameters. Yeah, so I guess the probabilities are like exponentially small, so I feel okay saying that it's just true, but yeah, that's the more correct statement.
Sure. Okay, yeah, thanks. We probably have time for one more question for Mark. I know he has to get off right at 2, but it's probably time for one more quick question.
I can ask a quick question. So great talk. My question is with respect to model pruning research. So how does your result connect with model pruning research, where they show that they're using overparameterization, but for model specification, right? Dropping certain weights and these weights can be up to 95%. So any thoughts on that?
Yeah. So it's kind of interesting, actually. So initially we thought that our result was like suggesting this as a good thing to do. Just like not too long ago, we realized that the result actually holds where the number of parameters is the number of parameters you end up with, because like if you have a kind of a sparse function class, so you have p parameters but only k of them are allowed to be non-zero, then really the effective number of parameters is just the number of non-zero parameters, if you're thinking about like covering numbers and things like this. Yeah, so it's a bit so I think so. I guess my current understanding is that we don't say anything about why pruning afterwards succeeds.
Got it. All right.
Yeah.
Thanks.
All right, well, I think we can get you out the door right on time today, Mark. Thank you so much for a very interesting talk. If you have additional questions for Mark, I'm sure he would welcome an email for you for some further discussion that was started here today. So yeah, thanks for your time, Mark, and have a great afternoon, everybody.
Yeah, thanks very much. It was a lot of fun.
Yeah, bye.